All right, guys. So this is our last set of objectives for Unit 5, and this is going to be a 2-day objective. Today, we're going to do the word problems that are base 10, the common log, and tomorrow we'll do the natural logs. So today we're going to study logarithmic function application problems for electrical engineering, and I'm going to focus today on like amplifiers. So like you were going to plug your guitar into an amplifier. So there's a formula that goes with that. And then we're going to study also a little baby study of geology. And actually it's kind of an obsolete study. We're going to study the Richter scale, which is the magnitude scale that we used to use to measure earthquakes. But there's a newer scale that is more precise that we use, but it doesn't use logarithms. And since we're studying logarithms, we'll still talk about it. There's still some validity to it. We just don't use it anymore to measure how intense a magnitude is an earthquake. So this is what we're going to work on today. So we're going to start off with electrical engineering. It's a subcategory of electric engineering. This is a base 10. And we are looking for the powers. When we solve these, we're looking for what power are we raising 10 to get to our voltage. So engineers use the common logarithm to measure the voltage gain of devices such as amps, amplifiers, or the length of a transmission line. How far does the voltage travel? Okay. The unit of gain. Sometimes it's a unit of loss. Sometimes it's a loss. If you get a negative answer, it's a loss. Okay. If you get a positive answer, it's a gain. Is called the decibel. Okay. And it's defined as a logarithmic function. So we like the logarithmic function because it helps us to determine the decibels, which I believe, okay, you can tell me if I'm wrong because I'm just a math teacher. And I haven't taken a science course in a long time, but I'm pretty sure decibels measure sound. Okay, thank you. You know, because you're in science class. All right. So here's the formula that we will be using for our decibel gain or loss, PS or loss. All right, so I'm going to color code my work here. dB, that's not a B. dB is the decibels. In gains or losses. So that's what we'll probably be looking for. E, I'm switching colors. E sub O. By the way, that's not a 0. That's the letter O. So it's not the initial. It is the voltage output. O for output. E sub O is voltage output. And when I see E, I think energy. And I'm wondering if it's that same category, if it's the energy output. I'm not sure. E sub I. That's an I, not a 1. What do you think that is? You got it. Voltage input. And the problems that we will be solving will be giving you 2 of these 3 pieces of information, and you will just be solving for the missing piece. Okay, so I'm going to read my problem, and I'm going to pick up my colors, and I'm going to mark my text to match my colors. So it says, find the decibel gain. So what am I looking for? Oh, that's the wrong color. That's purple. Try purple. Go back. Thank you. Pinkish purple. So that's my unknown. So I'm going to name it X because that's what I'm supposed to look for. The decibel gain of an amplifier, find it if its input, which I did in green, if its input is half a volt, so I'm going to circle that. That's my E sub I. And its output is 40 volts, so I'm going to switch to blue. 40 volts, that's my E sub O. So basically, I can plug that information into my formula here. And I think what I'll do first is I'll write all of the stuff that's constant. We know it's going to equal 20 log. And I'm going to do a division here. Find the quotient of these two things. And then I'll color code. So X is equal to my E sub O in the numerator. So that's 40 over my E sub I of half. Now I'm going to ask you a trick question. Think before you answer. What's 40 divided by half? It's 80. 40 divided by 2 is 20. 40 divided by half is times 2. Yeah, instead of dividing by half, you multiply times its reciprocal, times 2. Okay, so you're going to plug that into your calculator. X equals, and just plug it in. 20, you don't have to use multiplication symbols or anything. 20 log, get your fraction, 40 over 0.5, or you can do 20 log 80 if you want. 38.0618. So when you hear decibels, and you've done problems with these before, maybe in science, do we mention the extra parts of a decibel? We don't. We say about 38 decibels. There's your answer. And is it a gain?
Yes.
Yes, because it's positive, so it's a gain. So it's a 38 decibel gain. So did it get quite a bit louder? Yeah, quite a bit. All right. Now let's try the next one. It says find the decibel gain if the input is 0.7 of a volt. So here's what I'm wondering. Prediction, is it going to be louder or is it going to be softer? Okay, test it out. Let's see. Test your prediction. So 20 log 40 over 0.7. 35.1392. So you had more input, but you didn't get more output. So the gain is, it didn't gain as much. So it's a less gain. So it's about 35 decibels. You had more input, but you didn't get more output. So it didn't gain as much amplification in its decibels. Okay, so you'll get some problems that will ask you questions similar to that. You'll get a couple where you might, or one or two where you might have to find a decibel loss. All right, now let's talk about the Richter scale. So I want to point this out to you really quick. I remember learning this in high school, and I thought it was so cool because it really blew my mind and made me understand powers of 10 in real life. So the Richter scale, which is not what we use anymore, because after you get to like 6.5 or somewhere around there, it stops being really precise. So we now use the moment magnitude scale instead. You know how through science and through time, people get better and they refine. That's what's happened here. So anyway, if you are on a Richter, this is every value is 10 times bigger. So if we're getting an answer of 1, a 1.0 on the Richter scale, okay? Okay, forget what I said. We're starting over. All right, so basically what this means is that every time you move up on the Richter scale, 1 whole unit, each level is 10 times stronger than the prior level. So if it's a 1.0, it's a really tiny and you're not going to feel it. If it moves up to a 2.0, it's 10 times as intense as a 1.0. And as you move from a 2.0 to a 3.0, hello, it's 10 times as intense as a 2.0. So how do I compare a 3.0 to a 1.0? How much stronger is a 3.0 than a 1.0? 100 times. So how do you think I could compare a 1.0 to a 10.0? 10? No, 2 is 10. 100, 1,000. 5 is 10,000. 100,000. Million. 10 million. 100 million. Billion. So a 10.0 is 1 billion times as strong as a 1.0. And 1 billion has how many zeros? 9. So a 10.0 is 10 to the 9th power. Okay. So I just always thought that that was crazy, that as you jump up one number on the scale, your magnitude or your intensity gets 10 times as intense. You start feeling earthquakes around 4-ish, a 4.0. They get scary once you hit the 7.0s. And you don't want it to hit a 9.0 because this building would crush us. Okay, Jesus, we don't want any of that. Okay, moving on.
What does it say at the bottom? Does it say really on the other parts? What does it say for 10?
It's extreme every 1,000 years. Rarely happens. And we don't call them 10.0s anymore. Like 8.9, I think, is the top. Anyway, I can't remember. Don't quote me. Don't quote me. I hate to even put this out on the YouTube, on the interwebs, because if I'm wrong, people are going to get all over me. I'm glad nobody subscribes to my page. All right. My YouTube channel. Okay. So, anyways, let's go. It's okay if you guys do. It's okay if you guys do. Okay. Anyways, so we're going to study this. Seismologists measure the intensity of, okay, let's change the wording. Used to measure the intensity of earthquakes on the Richter scale, spelled R-I-C-H, spell rich, T-E-R, Richter scale, which is, I can spell, is a base 10, which we just looked at. Okay, so this is another example of the common log, okay, because it's a base 10 log. And what we'll be looking for is what power are we going to raise 10 to determine its magnitude and intensity. So that's what we're looking for. What's its power? Its magnitude. So we're going to come over here and look at the formula. R is the magnitude of intensity, which, you know, R is the Richter scale, which measures the magnitude. Okay. A is the amplitude, which I'll try to explain, hopefully somewhat clearly here, in micrometers. You know, micrometers aren't very big, right? Like, they're super tiny. Micrometers. Amplitude looks like this. If you were to look at a the seismograph, I think that's what it's called, it has a little needle on it, and then little needle sits on a piece of paper, and if there's an earthquake, it'll shake the needle and it draws, and it'll show you this. So you'll see this happen like that, and then after it starts to settle down. Amplitude is measured on the tallest jump. So this is what you consider your oh, let me do this with a different color. This right here, this measure is what my understanding of the amplitude is. How much of a jump did that needle make? Okay, so that's amplitude. And then P is our period. And this is measuring time. And so it's in seconds. And basically, what it's measuring in seconds, I'm going to stretch out my amplitude here to just this little section right here where it goes like this. Okay, pretend I did a really good job drawing that. The amplitude is the height. The period is how long does it take the needle to get back to its starting position, how much time. So this right here, from base to base, right here, this is what we would call a period. How long does it take the needle to get back to its beginning position? Okay, so that's all we need to know, and we need to know it's base 10. So what we're doing is dividing the amplitude by its period, and that's going to tell us how powerful in magnitude our earthquake is. All right, so let's go do this problem real quick. I'm going to pick up my purple pen because that's the first thing I'm going to do. Find the intensity of the earthquake. So that's my X, right? My magnitude. How intense is it? If it has an amplitude, I did that in blue, an amplitude of 500 micrometers, which look at that, that's only half a centimeter, tiny, and a period of 7 seconds. 0.07, 700ths of a second, thank you. All right, so we're just gonna plug that in. So I know I'm doing equals log of something, so I did that with my pencil, just color coding here. So purple please. X is equal to log base 10, we talked about that, of 5,000 over 700ths of a second. Plug it into your calculator just how you write it. And do you think it's a very big one? Think you're going to feel it? Half a centimeter doesn't feel like very much, right? And 700ths of a second isn't very long. What answer did you get? 4.81. So 4.9. When we measure Richter scales, and I think even with moment magnitude, we measure them to the tenths. So it's approximately 4.9 magnitude. And that's on the Richter scale, not on the moment magnitude scale. Okay, so probably you're going to feel it. Maybe if you're asleep, you won't. If you're a good sleeper. All right, let's do the next one. Find the intensity of an aftershock. You know what that means, right? Yes. Okay. With the same period, so what's our period? 0.07. So I'm going to write that down, 0.07. But 1/2 of the amplitude. 1/2 of what was the original amplitude? 5,000. So what's half of that? 2,500. All right. So that's our A. So all we got to do with our calculator is copy paste our original problem, but change 5,000 to 2,500 and hit enter. Do you think it's a lot smaller? Got a prediction? X equals 4.6. Doesn't seem that much smaller. But maybe at a power of 10? I don't know. What's the difference between 10 to the 4.9 and 10 to the 4.6? Could you plug them into the calculator and tell me how different are they really? Are they really that far apart? 79,432. And what's 10 to the 4.6? 39,000 what? 810. Look at that difference. Isn't that crazy? And it's only 0.3% difference. That just goes to show you how powerful a power of 10 is. So I think that's a pretty cool little comparison to look at. All right, so today your assignment is, we'll finish this tomorrow. So today you're going to do problems 1 and 2, problems 7 through 14, and problems 23 and 24. And 23 and 24, you're going to have to figure out. There's some data that'll help you. You won't have a problem. I believe in you. I believe in you. That's what I'd like you to do. I believe with 14 minutes left of class, you can get it done.